These are two white dwarfs in a binary system, and these two white dwarfs are only 50,000 miles apart. Okay, that's less than a fifth of the distance to the moon. They are orbiting every 5 minutes. They're going 1,000,000 miles an hour. Their orbit is decaying by slowing down, decaying by 1.2 milliseconds a year, which means they're moving closer towards each other by 2 feet a day. So eventually, these two white dwarfs are going to come together. In the meantime, if you're losing energy in one place, you have to gain it somewhere else. Delta E always must equal 0. And so it is thought that this system must be producing some really nice gravitational waves. If we ever do get a mission to detect gravitational waves, that's the only Einsteinian theorem that we do not have direct evidence for yet. We have not yet caught that wave. This would be a great place to look. As it happens, the mass of these two are one's like about 0.4 and one's like about 0.6. So when they coalesce and come together, they still will not exceed Chandrasekhar's limit of 1.4 solar masses. So it will simply be a one more massive white dwarf. Here is another system which has been detected, and these two white dwarfs are even closer together. And one of them is enough more massive than the other that it's actually drawing material from its companion white dwarf and setting off little thermonuclear events on the surface. And this particular one, a couple of different things could happen. They could coalesce and become a neutron star, because it would exceed Chandrasekhar's limit of 1.4 solar masses when these two get together. But unless you have more mass than 2.4 solar masses, you can exist as a neutron star, so they would become a neutron star. But this is a pretty unstable system here, and this might pull enough material off at some point in time. This could actually become a Type 1A thermonuclear explosion, so a supernova event with a Type 1A supernova remnant left behind. Chandra's legacy eventually probably is going to be all of the work it's done in the center of our own galaxy and trying to understand our own massive black hole, about 3 million solar mass black hole, not too massive not very massive as black holes go, actually, but that's okay. That's actually a good thing. So Sagittarius A is, it was thought that in the accretion disk around Sagittarius A, or within like 5 light years of Sagittarius A, they might find 2 or 3 black holes. However, they detected within the accretion disk around Sagittarius A swarm of more than 10,000 black holes. And there also seems to be, in studying the accretion disk around Sagittarius A, it seems to be that for some reason in this really hostile extreme environment with this incredible gravitational forces and the magnetic friction forces somehow sets up a scenario that favors massive star formation. So massive stars are actually forming in the accretion disk around Sagittarius A. And massive stars, you know, have a quote, short lifespan of a few hundred or tens of millions of years and become black holes, and that's why that population is there. This is a recent observation of Sagittarius A right here, focusing in on the jet. Chandra is trying to determine the position and length and the energy of the jet from Sagittarius A, and the radio are shock waves being produced by that jet, and those are radio data. This is the halo surrounding the Milky Way galaxy. Now when you see photos of the galaxies, halos around galaxies, you see them like right around. The diameter of the halo is pretty much the diameter of the disk of the galaxy itself, so it would be sort of like there. But look at how much halo material there is. Now, see those 2 objects in there? That's actually the largest small Magellanic Cloud. They're within the halo of the Milky Way galaxy. They're 160 and 190,000 light years away. There's more mass in the halo of the Milky Way galaxy than there is in all the stars in the Milky Way galaxy. I remember when there used to be, the missing mass of the universe. How can it hold itself together? 90% of the mass is missing. Well, of course, that was just undetected mass, as we detect more and more all the time. This is ARC 220. This was part of a survey which showed that the more energetic a galaxy is, the more massive its center black hole, the more energetic and jets that it produces, the less star formation that goes on in the galaxy itself. That's why it's a good thing that the Milky Way has a kind of a wimpy little black hole and jets. That means there's lots of star formation going on for us. This is Hercules A, and this is a really, really energetic galaxy. And all of this purple is hot gas, X-ray emitting gas that's been heated by the infall of material into the black hole in the center of this galaxy. And the blue, that's radio data showing the jets of material streaming away from the center of this galaxy. And that jet is 1,000,000 light years long. Incredible. But here's my favorite one of all time. This is 3C321, and this is a galaxy and a companion galaxy. And to see what's going on here, you have to see the animation. This is a really nice, energetic galaxy with a very large jet of particles coming from the black hole in the center. And as we get further and further away from the center of that, we can see the galaxy itself now. And here's the jet. And up here, this is the companion galaxy. And that companion galaxy, about 1,000,000 years ago, actually ran into the jet being produced by this galaxy. And when it did, it actually hit and refracted away from that galaxy into outer space. Now, how would you like to be on a planet orbiting a star right there, where you're being bombarded by high energy particles? The distance between the two galaxies, this is 20,000 light years away, and this jet extends into space another 850,000 light years. This is Perseus A, which is a massive black hole in the center of a whole group of galaxies. And this stuff right here is the debris of an entire galaxy that's been torn apart by this black hole. And you can see here sort of some kind of structure. These are called cavities. They're very interesting cavities. So here are the cavities. There's a torn apart galaxy, poor thing. And you can see out here some other kinds of odd structures going on. Well, I was very disappointed when this press release came out because it said the sound of a black hole. So I thought I was actually going to hear what a black hole sounded like. So I told them they shouldn't have fooled me like that. So what is going on here, here's the cavity. And then what these are compression waves, and sound waves are compression waves. The only problem is these compression waves are 50,000 light years apart, which makes them B flat, but 57 octaves below middle C, which is 1,000,000 billion times lower than the human is capable of detecting. So I still do not know what a black hole sounds like. And Perseus is also being studied a lot, as with any galaxy that has these cavities, because with all those cavities, they would have cool gas in them, a lot of cool gas. And you need cool gas for star formation to take place. And there should be tons and tons of star formation taking place in these cavity regions around these active galaxies. So, but there's no star formation. But they have determined by looking at Perseus And by looking at the Virgo cluster, there's actually an incredible amount of turbulence taking place within those cavities that's stopping star formation from taking place. And this incredible spiral galaxy, I love this one, it is moving through space-time at about 5 million miles an hour. And as it is being subjected to what is a process called ram pressure stripping. As it collides with the interstellar medium puts pressure on it, and actually, as it moves through, it strips the gas and the dust away from the spiral galaxy, and it trails along behind it. And that is lowering the potential for future star formation in that galaxy. Less and less all the time as more and more material gets stripped. But that's counterbalanced by something else. You see these long tendrils. It's kind of like a jellyfish with these little tentacles, tendrils kind of trailing down. You see these long blue tails of blue dots. That actually, the same process that's stripping the galaxy of its gas and dust is causing star formation to form. So these are strings of stars being formed in the trailing wake of this galaxy as it plows through the interstellar medium. This is the Sculptor Wall. It is a massive wall of galaxies. Galaxies are in walls and strings and embedded within a gas that's called WIM, weak hot intergalactic medium. And it actually produces an X-rays, but we can't detect them because it's very, very low. So in order to determine or try to get a measure of how much mass is in this gas surrounding all these galaxies, Chandra looks at things like quasars on the other side of the wall, and then they just look at the absorption lines from the quasar as it moves through that gas and dust. That allows them to actually determine the amount of mass that's in the wall and actually help them construct where the gas and the dust is, and therefore help determine the total mass of the galaxy. All of the objects that you've seen in this presentation were all analyzed, studied, researched using the DS9 image analysis software tools. That is the software that the scientists use. It is also available for you to download and use on any platform, on a desktop or a laptop. It works with Windows and with Mac. And what it does is when you use the analysis tools, you can pull down, for instance, CAS A. This is what you can download a little toolbox onto your desktop and drop in CAS A. Here's CAS A. And you can use all of the analysis tools that the scientists use, because when you ask it to do an analysis for you, it actually sends that back to a server farm, either at Rutgers or at the Smithsonian in Cambridge. And the analysis is done in Linux and sent back to you. So it makes your machine a virtual Linux machine. And also, I am understanding that they have gotten there or are close to getting there, or maybe they have done it now. They're making that a browser-based tool so that you don't even have to download the toolbox anymore, that you can just do it through the browser. And we have a whole series of activities using DS9 on the Chandra website in the educational section if you would like to use this material in the classroom. So, and here is the request if you want to request materials from the Chandra X-ray Observatory. As I said, on the educational website we have a lot of materials on stellar evolution and stars and variable stars. And if you want, and we also have on there webinars for Science Olympiad. If you are interested in Science Olympiad, there's a lot of materials there for that. And if you want this actual PowerPoint presentation, just send me an email, donna@aabso.org, and I will send you the PowerPoint that goes along with this webinar. So that's Chandra for 2015. Thank you.